Hi, my name is Miranda Magdaleno. I'm from Math 12, Section 5D, and I'm going to be presenting a presentation of practical use of differential equations, more specifically towards ecological models. So what is differential equation? So differential equation is relating to one or more functions and their derivatives, and it defines the relationships between two. So how do we use them in class? So we defined differentiation as an ODE is an equation with derivatives, and a solution to one ODE is an equation in which, when plugged into the ODE, yields an identity. So how do we use them in the real world? So we talk about differential equations as a decay growth rate in the population or of a disease, the movement and flow of electricity, motion of object to and for like the pendulum. So what is a population growth rate? So a population growth rate, it's a rate at which number of individuals in a population increases at a given time, and that would be the equation for the population growth rate. N would be the population size, T would be the time, R would be the rate per capita. So how do we distinguish between exponential and logistic growth rate? So for exponential, it'll be when the per capita rate increases, takes the same positive value regardless of the population size. And for logistic would be the per capita rate decreases as the population increases towards the maximum limit, and the maximum limit would be called the carrying capacity. So what is a growth / decay? So when we talk about when the population grows, so it's basically increasing in the number of individuals in a population, and then when we talk about decay, is a decreasing number of individuals in a population. So Perry, Franquist, Verhulst proposed a logistic model, and that would be the equation that he proposed, and then n would be the maximum size of population, and the right side can be presented as that equation. So exponential versus logistic growth rate. So this would be the two distinguishing factor. So visually we can see that the growth rate, exponential growth rate, would be the increasing population size, and then for logistic would be that it's increasing but then it reaches carrying capacity, would be the K. So how do we talk about exponential decay in class? So this is a problem that we did in class to relating exponential decay. We talked about how the coffee temperature was at 70 and then the room temperature be 20, and assume that K equals 1/8. So how do we find in any given time the temperature of the coffee? So we have the differential equation, the derivative would be 1/8, the time frame, and the temperature at 0 would be 70 degrees. So we plug it into the equation, and then once we solved, we got that lasting equation, and then I plugged it into the graphing calculator and got that graph. And you can see that the population is decreasing. So logistic problem that we did in class, we did a problem about frogs in a pond. So the frogs in the pond is a 5% growth rate, and the initial population of frogs would be 1,000, and the carrying capacity would be 6,000. So what is the population in a given time? So we have our rate, which is half. We have our carrying capacity to be 6,000. We have our population size of 1,000, and then we have our equation for logistic problems. So we plugged it in and then solved and then got that equation. And then I plugged that equation into the graphing calculator and got the graph. I could see that the logistic will be that. So this is my citation of all the sources that I got in order to do my presentation. Thank you for listening, and I hope you enjoyed.